So hello everyone and welcome to the third session of the 4 Cs by Desh and welcome. So Desh, over to you.
Okay, thanks Priya. Good afternoon to everyone who has still patience to listen to this. This being the last talk particularly. Okay, so I think we had looked at convolution in great detail. Also the Fourier transform aspect. We will continue with some aspects relating to additional dimensions. So far we've been looking at patterns which are one-dimensional. Whatever considerations we had, even the definition of the Fourier transform and so on, will apply equally well with multi-dimensional data. And here is a example of a square aperture, which we know the aperture distribution relates to the far field diffraction pattern of this aperture. And that, knowing that in each dimension it's a rectangular function, in the corresponding dimensions, you will find that the 2D pattern, which is a Fourier transform of the square aperture, will have cuts showing sinc function profile. And since there is no circular symmetry here, of course, the pattern also will not have circular symmetry, but it will correspond to the net integrated version of this 2D aperture in any 1D. If you take a integration, then you will get a 1D pattern, and you can confirm that its Fourier transform corresponds to the corresponding cut of this 2D picture. This is just a sanity check. Okay, so and the power pattern, of course, will be square of this, so it will be a 2D sinc square, and then you, with your knowledge that that the squaring will result in self-convolution in the other domain, in the aperture domain, you can imagine that what effective aperture distribution that it would correspond to, and convince yourself that it will be a pyramidal function. So while rectangular function, square aperture gives you a field pattern of 2D sinc, 2D sinc square will correspond to self-convolved version of a rectangular or a square aperture, which will be pyramidal function. You can imagine that when for zero shift, the entire volume of this function is common, and then it will taper off as you slide it by an amount when it becomes comparable to the width of this rectangular square aperture, you will get no overlap, and that will go to zero. That's a pyramidal function. Okay, let's come to correlation formally. Correlations are, as I said, are tools to examine similarity. We have seen the familiar context of linear regression and line fits and so on, and what we are trying to do is exactly what we can compute formally through these equations, where we can compute a cross correlation measure. We can even normalize it with the certain properties of the variation that is to be examined in both the functions that we have, and that is characterized by the typical standard deviations. We also do not want the mean values of these functions to play any role in the correlation, because if there is, when you take product of two functions, you will always get product of the mean values. But what we're interested in is the variation represented in the function, whether that pattern is correlated with or has any relation with the pattern in the other function. And that requires that we remove the undesired contributor potentially, which is the mean value of individual functions. And so you will see that after each one of these terms in the numerator is basically a mean removed version of the function. Let me move this so that I can see what you're seeing. Okay, and then you can shift one version, one function with respect to the other, and see the level of similarity. And as you will see, it's divided by the square root of the variances of both these functions. Variances square root is simply the standard deviation. And so each one of these functions is normalized, if you like, by their mean subtracted, normalized to their respective standard deviation. It becomes a measure which is independent of the actual absolute scaling of these functions. So because we are interested in the level of similarity as a sort of percentage similarity or fractional similarity. Okay. As you will find, any pattern detection is tied up with the method that you adopt. You will find that if you were to see if some pattern is matching with the other, you will have that template pattern that you want to seek match with, and you will want to compute this correlation. And ideally, what we are trying to look for through the shifts and so on, that we want the autocorrelation function to be realized. So, for example, if there is if the function that we are looking at in the presence of a whole lot of things also contains the pattern that we are looking for, then you can simply write the other function as some scale version of the pattern we are looking for, plus some thing which is everything else. And then when we do the cross correlation, you will find that it will not correlate with the other parts of the pattern. And what we will get is something which is a scaled version of the autocorrelation function in some sense. And that is why autocorrelation function is the desired one, because it basically represents the autocorrelation peak, represents the full power or energy associated with that pattern. And that's the best measure that you can extract of the hidden pattern, and you can see its contrast with the rest of it to make a detection. As we said, we have devices which do the convolution, and physical devices which can do the convolution, and correlation is something that we perform with hands. So, but you can get a device which knows only how to convolve to perform a correlation if you present to the convolver a property that its spectral characteristics or impulse response, which is a Fourier transform of the spectral characteristics, has conjugate relationship with the pattern you're looking for. Okay? So you can design such, after all, convolution is a filtering operation. You can design such filters. And one very good example of I used to actually give very complicated examples, analogies earlier, and one of the students like you actually suggested to me, why not, this is the simplest analogy. So the analogy is, if you're trying to look for a match between two keys, how would you, what is the most practical way of approaching it? Is to get hold of a lock which the key can open, and then see if the other key also is able to open the same lock. And this is exactly what is done in the conjugate filtering operation. Our lock is this device which knows how to convolve, and you give it a property of the conjugate pattern, which is nothing but the lock. So you can see whether the two keys, how similar those two keys are. And in this particular case, of course, the details will not be measured. You will just know the answer in terms of whether they match or don't match. We will find that in almost every processing that we do, and every step in data reduction that we do, in order to look for the entity that we are interested in, we land up doing optimum filtering, and optimum filtering is most optimum when it's matched filtering. Be it doing while doing the pulsar search or other study techniques, you can see examples of this coming through. When people say in the pulsar search, they fold the data at different periods and see which one gives them good signal. They're actually doing match filtering. So whether you admit or not, or whether you realize it or not, if you're doing the right things about any pattern recognition or processing of the data to bring out the features, hidden features, and detect them, you are doing match filtering. Okay, before we go further, since we have talked about Fourier transforms, it's important to stress that there is no point-to-point mapping of from one domain to its Fourier counterpart. And this is I'm saying this purposely because people often mistake this aspect. Suppose you see a feature in your pattern at hand of which, let's say, delta x. That doesn't mean, and if it's nice and tall, that doesn't mean there is a discrete contribution, tall contribution or recognizable contribution at frequency, which is 1 upon delta x, or a Fourier component at 1 upon delta x. Remember that every point, you saw the integral, every point in one domain is contributed to by all points in the other domain. So you can, of course, see how they are contributing to a particular, suppose the peak, that one discrete feature that one just talked about in the X domain, will be contributed by all spectral features. Of course, what it means is the phase relationship is such across all the parts of the spectrum that they cohere to produce that peak. Certainly that information can be used and profitably some.
No, ma'am, it's not fine.
The audio is gone. Right? Have we lost Desh itself? Yeah. Okay, so then just hold on. He'll be back. We've lost him. Should I stop live stream? There's no pausing. That's the problem. Hello, I think we've lost Sir. Just hold on. We're just trying to contact him. Continue. Anyway, there's a gap.